you for introduction. I'm very happy to attend this conference, and I'm very happy to see that many people are now interested in orderable groups. Okay, so let's take my talk. My talk is about the generalized torsion element, a generalization torsion element. So it's almost a synonym, but let us start. So main objective of this conference is, of course, ordering, say left ordering and bi-ordering and left orderable groups and bi-orderable groups, and of course, and there are many other kind of orderability property issues that like circular ordering, the local invariant ordering, and so on. But I mainly did just concentrate on these kind of very simplest, the simplest and the most standard orderable structures of groups. The first lesson is that it is elementary fact. If group Z is left orderable, then Z has no torsion element. That means that if some powers of if some powers of Z is 1, then Z itself is an identity element. Why? Because assume that Z is greater than 1 for some left ordering, then multiplying Z square is greater than Z, and so on and so on. So the lesson is that when we study left orderable groups or something like related topics, okay. This is
the definition of left ordering, do you have the correct thing?
Okay, so please correct that DB. If you notice that my misspelling, please let me know. Maybe I made a lot of misspelling. Okay, so anyway, the lesson is that if we are studying a left orderable group, then we naively assume that the group is always torsion free. So for me, group is always torsion free group. And the thread is different. As a generalization of torsion element, let us introduce the main object, the generalized torsion element. So a non-trivial element Z of a group is a generalized torsion element, then Gx1 is 1. Here Gx1 is not a power, but conjugate by x1. So it means that some product of some conjugate is equal to 1. This is a counterpart of the torsion freeness for bi-orderability case. Namely, if this is bi-orderable, then they have no generalized torsion element. Again, the proof is similar. I mean that assume that this is greater than 1. No, since this is bi-ordering, so conjugate by taking conjugate, it remains that this conjugate by x1 is still greater than 1. So taking product of conjugate of Z is always greater than 1. So bi-orderable groups have no generalized torsion element. And so, of course, this equation says that the generalized torsion element is a kind of generalization torsion element. Namely, if we take x1, x2, xn, or just a trivial element, then it just says that the power of Z is 1. So as a natural generalization of the notion of order of torsion element, let us consider the generalized torsion order. Namely, the minimum length of number of conjugates that to make the product to make equal to 1. Here, this quantity is often called the order of generalized torsion, but in this talk, I emphasize that to call that this is a generalized torsion order because in general, the order of the torsion element is not equal to the generalized torsion order. What does it mean? Here's an example. Let us consider the dihedral group like that. Then n's power is 1, so and one can check that the order of A is a torsion element and order of A is n. On the other hand, but the second relation, A conjugate by B and product of A is always 1. This says that generalized torsion order is 2, so the difference of usual order and generalized torsion order can be arbitrarily large. I briefly recall several related notions. So a group is R group if this power is equal, then A is equal to B. And alpha group is some kind of generalization, say Ax1 that Axn is equal to Bx1 that Bxn, then A is equal to B. Why these properties are related? Because first, R group can be understood as a torsion free and some kind of high powered commutator. Powered commute means that always original element commute. And this property is important because A power and B power commute implies that A and commutator of AB is always a generalized torsion if it is non-trivial. So R star group has no generalized torsion. And it is some easy exercise of bi-orderable group. It's always R star group. R star group is always R group. And the converse is not true. To me, to us, it is important that a group, this definition is similar to the generalized torsion element, and a group Z, it is easy to check that the group is an R star group if and only if they have no generalized torsion element. So R star group can be understood as a generalized torsion free group. This is just a comment, but in a relation to the dynamical realization, if G is left orderable, and if we take a dynamical realization left ordering, then general and assume that rho Z is monotone increasing. Then G is not a general torsion. So this indicates some relation to the left orderability or dynamics and generalized torsion element.
Don't Tetsuya, sorry,
Okay.
I don't understand. Because in any left order, these are monotone increasing, you know?
Monotone increasing just means that say the X is always monotone increasing, it means that
Okay.
or monotone decreasing. So now let me explain why I not we why I take care of general torsion element. First of all, as I mentioned, general torsion element does not exist for bi-orderable groups. So checking generalized torsion element, whether general torsion element exists or not, gives a useful criterion to check a given group is bi-orderable or not. However, in general, R star group without general torsion does not always imply that it is bi-orderable. So this direction is not true. However, in many cases, in many applications or in many theoretical situations, actually we are checking it using a R star property. So although the general torsion does not solve the bi-orderability problem, but knowing general torsion element is a first and useful step to study whether a group is bi-orderable or not. And also, like Rayleigh space conjecture, there is some. Okay. R star also problem is that so we know that BO implies R star. It is okay. It is easy, but the converse is not true.
Yeah, I mean, if we are not implied then bi-orderable, we also imply that orderable.
No, I will talk shortly. So the problem, and as for the relation to the low dimensional topology, there is some interesting conjecture due to Motegi and Tetsuya Ito. They conjecture that for three-manifold group, bi-orderable is equal to the R star. That means that non-existence of generalized torsion elements. Why this is interesting? Because the most three-manifold groups are not bi-orderable. Indeed, it is quite rare that bi-orderable three-manifold groups. So, in light of this conjecture, there are many generalized torsion elements in three-manifold groups, but currently, our knowledge is very poor. We have only small examples of generalized torsion elements in three-manifold groups. So, investigating generalized torsion elements in three-manifold groups is an interesting topic. Also, generalized torsion element is interesting to dynamics of left orderable groups, and here's an open problem. And R star group is LO or not. This is as long as I know, it is an open problem. The main aim of this talk is an advertise the generalized torsion element is a good object to study. There are many interesting and natural questions which are not investigated yet. So let us proceed to some second chapter. So general torsion element versus torsion element. I mean that I would like to discuss the following problem. So torsion element is a natural class of group element, and there are many studies on torsion groups, and torsion elements have some very special properties. So so besides orderability properties, let us forget orderability. Just look at the generalized torsion element. As its name suggests, it is a generalization of torsion element. So it is natural to investigate, say theorem. If group, let G be a data data group, then torsion element of data data group is a form data data data. This kind of theorem is ubiquitous. So it is natural to try to extend theorem like theorem about torsion group element to generalized torsion element. For example, the study the property of generalized torsion element in general. I mean that for orderability problem, it is just important that whether there exists a generalized torsion or not non-existent. However, it is also useful to look at general torsion element itself. Say for a given class of G, can we classify general torsion elements? This problem, of course, makes sense and interesting for groups with torsion elements. So my first step is that let's consider the group and possibly possibly contains torsion. Then try to what extent the property of torsion element can be generalized to a generalized torsion element. So I just present one natural example. Let us call a group as a TR star group if generalized torsion element is actually a torsion element. I mean that I said that a torsion element is generalized torsion element, a generalization of torsion element. But let us call the group as TR star if such a generalization is meaningless. Of course, I think that it is a natural class of group. Let us try to think of which groups are TR star group. Of course, R star group, which is this is just a torsion-free TR star groups. In the opposite extreme, let us consider torsion group or periodic group. I mean that every non-trivial element is a torsion. Then, of course, every element is a torsion element, so every generalized torsion element is torsion element as well. So these are somewhat trivial examples. And again, almost trivial example is the abelian group. But abelian groups are slightly interesting because that can contain both torsion and non-torsion elements. The next class is the generalization for locally nilpotent groups, again a TR star group. This is observed by Bastov, Schneider, Silver recently. In a slightly different direction, FC group. This is a group, every element has finitely many conjugacy classes. I don't know much about it, but such a class of groups has been studied because it is a generalization of finite group. So certain kind of finiteness condition. Then such a group is also a TR star group. So natural question is that what is a TR star group? Every conjugacy class is fine. The reason why I call such a group TR star group is due to the following theorem. A group is TR star group if and only if it is TR star group. I mean that torsion T by R star group. Yeah. At the first time I thought this group as a no trivial generalized torsion group or something like that. But I found that since I found this theorem, I decided to call this theorem as this class of groups as a TR star group. Namely, there is an exact sequence 1K, ZQ, such that K is a torsion group and Q is an R star group. Indeed, this theorem is very easy to prove once you recognize this following simple property. Assume that A and B are torsion elements. In general, product of torsion element is not torsion. But fortunately, product of torsion elements are generalized torsion elements. Of course, we assume that general torsion element is non-trivial, so its product is non-trivial. This is not hard to see. Assume that A power of n and B power of n is equal to 1, then consider the product AB and suitable conjugate of AB. The trick is that this part becomes the B power n, so they cancel. Then after taking suitable product of conjugate, we get A power m and B power n minus m, and A power m is all trivial, so B power n minus m. So by repeating this part appropriate time, we get conjugate of AB is trivial. So, so proof theorem is not hard. Assume that Z is a TR star group. The following previous lemma says that the product of torsion element is a general torsion group. But we are assuming that the group is TR star, which means that the general torsion elements are torsion. This means that the torsion product of torsion element is again torsion. So the set of all torsion elements forms a group, actually normal subgroup. So let us model out the torsion group and consider general torsion element. What we need to prove is that the Q is the quotient group is R star group. So assume to the contrary that this quotient group has a general torsion element. So we get the general torsion equation. Then we taking some pullback. Then its pre-image, suitable pre-image is lying in the kernel, which is the torsion group. So its product is again the trivial element. So G is a non-torsion general torsion element. This is a contradiction. The other direction is also easy to prove, but just taking a torsion by R star group and assume that G has a general torsion element by taking an image by P. PZ is 1 because Q has no general torsion element. This means that G is a K, but a K is a torsion group, so general torsion element is always torsion. So this argument, although this argument uses a K is a torsion subgroup, but a similar argument says that following kind of generalization. Let 1KZP is an extension. If the non-trivial element of K is a general torsion element, then the element of Z is a general torsion element if and only if its projection is a general torsion element, or it is a kernel of B. This means that this theorem means that K is a general subgroup consisting of general torsion elements. So let us consider the following class of group. A group Z is a general torsion group if all the non-trivial elements of Z are general torsion elements. Recall the torsion group is a group whose elements are torsion. So this is a natural generalization, so it is natural to study. The previous theorem allows us to construct a general torsion group, which is not a torsion group. Here is a simplest example. Let us consider this kind of group. This is the extension of Zn by Z2. Thanks to this relation, every element of Zn is a general torsion group. In particular, infinite dihedral group is a general torsion group. And corollary, actually, this theorem, actually, this theorem says that general torsion group is closed as a group extension. This is some kind of generalization, well-known fact of torsion group because torsion group is closed as an extension. So, general torsion group is as a generalization of torsion group. It came up many natural problems which I cannot solve yet. Is there a torsion-free generalized torsion group? Currently, my construction uses some kind of starting from generalized torsion group, then we take some extension. But as a starting point, I need generalized torsion group. But I don't know no non-trivial examples. So I start from the torsion group, then extending them to get a general torsion group. So it is an interesting question that the torsion-free general torsion group exists or not. In a slightly stronger form, which may be easier to solve, is there a left-order generalized torsion group? Also, it seems that the generalized torsion group is small in the sense that it contains no abelian free group. And the last question is that find the characterization of general torsion group, like I did in TR star group. Of course, this kind of problem, if you think that it is easy to solve, then please add some additional assumptions like finitely generated or finitely presented or something like that to make the problem more interesting and hard. Here is one supporting evidence for the third question. A finitely generated general torsion group cannot be decomposed as a non-trivial free product. So it is indecomposable. Unless one exception, infinite dihedral group. Here I give a sketch of proof because it gives some useful insight. One trick is that if G is a general torsion element of group Z, stable commutator length is small. Here I do not explain what is a stable commutator length. What do you think that it is a magic wand? It is a well-studied object for the group, and there are many strong and useful result. But the property is, what we need to know is that there are well-studied objects or actively studied objects having many strong results, and stable commutator length provides an obstruction for generalized torsion element. In particular, if this is a generalized torsion group, then such a group has trivial stable commutator length. So such class of groups has been actively studied. Then using this, if group Z is a free product, then this group having a free product is very limited, and using some result of stable commutator length, we conclude that only the exception is the infinite dihedral group. All right, so then we slightly extend the following class of group. Generalized torsion group is a group whose element is generalized torsion. Let us extend the definition for subgroup. Namely, a subgroup H of Z is a generalized torsion subgroup if all the elements of H are generalized torsion elements of Z. Here, I remark that H, an element of H, might be not a generalized torsion element in H. In a bigger subgroup, in a bigger group, it becomes a generalized torsion element. Unlike here, in the previously, I mentioned that generalized torsion group has some strong restriction. However, it turns out generalized torsion subgroup has no such a restriction. Every countable group is realized as a generalized torsion subgroup of a finitely generated group Z. Indeed, we can do slightly stronger, namely, generalized torsion order is always realized as 2. This follows from famous HN and Higman-Neumann embedding theorem argument or result. So H is a generalized torsion subgroup of Z does not give any restriction. Contrary, if H is not a generalized torsion, if we assume that the generalized torsion normal subgroup, we assume normal assumption, then the situation is different. Here's one example. If H is not a generalized torsion group, such that an outer automorphism group is trivial, namely every automorphism is an inner, then H cannot be realized as a generalized torsion subgroup. Because of the conjugation, even if we embed H in the larger subgroup, conjugation action is just an outer automorphism and normal, so generalized normal subgroup. So there's some kind of restriction. It is interesting question to explore to realize a group as a generalized torsion elements. Okay, then I would like to proceed to the different topics, a generalized torsion order. So let us review the definition again. So this is the definition of generalized torsion element, and the definition of generalized torsion order is minimum n such that this equation is satisfied. And as I mentioned, generalized torsion order and order is different. So if we use a general group, then it is safe to use a generalized torsion order rather than to use order to avoid confusion. So just a convention. Let us regard generalized torsion order is infinite if it is not a generalized torsion element. Then we ask the natural problem. Let us determine or at least evaluate generalized torsion order of a given element of a given group Z. Compared with the torsion element, this problem is much harder. Why? Because to find a generalized torsion element, we need to solve this kind of equation. Z conjugated by X, G conjugated by X, X2, G conjugated by Xn is equal to 1. Okay, let us look at this equation. This equation has many variables. And these equations are non-commutative. So it is not easy to solve. And to me, what is most tantalizing point is that even if we know that we are lucky enough to find this kind of relation, and moreover, this is a prime number. When torsion element case, this solves the problem. because G power of prime P is equal to 1 implies that the order of G is P. However, as for general torsion element, this tells us only that general torsion order is at most P. So it can happen that P minus 1 or P minus 2 or So this kind of knowledge only tells us an obvious upper bound. So first of all, let us look at the simplest case, generalized torsion element of order 2. This is the easiest case, and generalized torsion order 2 element is easily classified. Let one G be a generalized torsion element of generalized torsion order 2. Then such an element is described as G is yx inverse, where y is a square root of x squared. I mean that x squared is y squared. So I mean that x squared is y squared. Then yx inverse is a generalized torsion element of order 2. And every generalized torsion element of order 2 is written in this form. This is just a simple computation, but I skip it. A point as a corollary, which is already observed by Himeno, Motegi, Teragaito, a group G has a generalized torsion element of generalized torsion order 2 if and only if x squared is y squared, but x is not equal to y. So thanks to this theorem, whether there is a generalized torsion order 2 can be solved, at least in some special cases. Unfortunately, when we try to look for generalized torsion element of order 3, 4, then we have no such a simple or easy characterization. So let us consider to try to explore some techniques to evaluate the generalized torsion order. Here is a very elementary first observation. So let N be a normal subgroup such that its quotient is a cyclic group of prime order. Assume that G is a general torsion element. Then, by taking the quotient map, this equation now becomes a very simple form. N times the projection of G is equal to 1 in the finite cyclic group of GQ. So this equation is very hard to solve, but this equation is very easy to solve. In particular, we conclude that PG is 1. This means that G lies in the smaller normal subgroup N, or the order N, this N divides N. It's divisible by Q. So by taking a quotient, and if we take some kind of good quotient, then we get the general torsion element should lie in a smaller normal subgroup or some non-trivial information about its order. This is, of course, an elementary observation, but it has some useful application. For every integer, there exists a torsion-free group and a general torsion element such that general torsion order is n. Because I'm just taking a kind of obvious, universal example. It may happen that G can be a general torsion order smaller than n, but by taking a quotient, we check that the order should be n. The lesson is that we use a certain kind of quotient to make the analysis of general torsion equation possible. So let us formulate this reduction procedure in slightly abstract way. Let us take R and H as normal subgroups of G taken so that this condition is satisfied. What happens then, since in R contains this subgroup, N over R is an abelian group. Also, since R contains N, commutator of H and N, G over H quotient group acts on N over R by conjugation. These two information says that we view that N over R as a GGT module just in this manner. The conjugate of Gx is by taking projection, it is a phi x, PG where phi x is a phi is a projection. This is some kind of abstract setting that means that takes some quotient and quotient. Why I take such a reduction? Because assume that in the situation like that, assume that Z satisfies the generalized torsion equation. By taking the projection, this equation forms to the following form. This means that in abstract form, we get the following criterion. Assume that G belongs to the normal subgroup N, is a general torsion element. Then let us consider annihilator of PZ. Here PZ is N over R. So some certain kind of abelian quotient of NR. This is a ZH module, and its annihilator idea contains a positive element, such that its augmentation is N. Here positive means that it is group link, so its coefficient is always non-negative integer. It's the simplest application. Let us take R and H as N commutator Z and Z. So H is Z, so ZH is just Z. So this abstract criterion says that N times of PG is 0. So in this case, we get a similar result. If G is a general torsion element, then PG is 0. Namely, G belongs to a smaller subgroup, or order of PG as a torsion element divides the generalized torsion order. So taking some kind of abelian quotient, we get additional information for the generalized torsion element. For example, by taking kind of a lower central series, we get we iterate this kind of argument to get, this is not cap. This is that roughly saying that a residual torsion free nilpotent or residual P with respect to Z, then its generalized torsion order is always divisible by P. But this formation is a bit technical, so I skip it. But what I would like to say is that taking some reduction and iterating argument, we are able to get some information of the order or generalized torsion elements. Here, I would like to explain the most useful case. Let us take the Rn reduction case, take and Z and K, where K is a kernel of the map from Z to Z. Those who know the Alexander polynomial just remind image that it is Alexander polynomial setting, as I will discuss shortly. Then, this reduction criterion says that Z is a general torsion element if and only if its annihilator ideal contains a positive polynomial such that evaluated at 1 is N. Here, positive polynomial means that its coefficients are positive, non-negative. So let us analyze what does a useful reduction mean. Generalized torsion element means if generalized torsion element, then annihilator ideal contains a positive polynomial of augmentation is N. First of all, annihilator ideal, although ZT is not a PID, if this ideal is torsion free, this module is torsion free, then annihilator ideal is a principal ideal. So we naively think that everything is a principal, though it is not principal PID. To me, everything is PID. Okay. So let us move to the second part. So this ideal contains a positive polynomial. What does it mean? Thanks to the recent result of GBCAS, we have a nice characterization of the ideal contains a positive polynomial. A principal ideal contains a positive polynomial if and only if its generator has no positive real root. So many of you notice that a similarity between the bi-orderability criterion for 5-word note as Dale's talk appears, or slightly generalized version for rationally homologically 5-word note case. If Alexander polynomial has no positive real root, then knot group is not bi-orderable. This is indeed this theorem is related to this kind of assertion, but I skip it. Anyway, what I would like to say is that this condition is just a condition of the existing positive real root on ZT. Finally, Moreover, we say that such a positive polynomial satisfies an evaluation of 1 is n. So using elementary arithmetic, we get that following kind of following lemma. Then assume that zt is da da da, then n, the value n satisfies the following inequalities. Although I wrote the proof, I omitted just say ft is an xt zt, some kind of positivity argument, just compute, just evaluate f1 and take appropriate inequality. Anyway, by summarizing the arguments so far, we get the following criterion. Assume that Z, let phi be a Z to Z map and H is a kernel, and N be a normal subgroup, and N over NZ is a torsion free. In this setting, if Z belongs to N is a general torsion element of torsion order N, then we have the following result criterion. Say annihilator is some kind of principal ideal generated some polynomial, and this general torsion order N is bounded below by top and left, top and bottom coefficient. And if N is odd, it is evaluated by f minus 1 absolute value, and so on. So the point is that under this condition, we have an estimation of N, general torsion order. So when we apply this kind of criterion for not case, then we get this argument. I omitted, but the previous argument is modeled on the Alexander polynomial case. Just I made everything abstractly to be able to apply general group case. Namely, if Z is a not group and let delta kt be the Alexander polynomial, then if not group has a general torsion element, then we have the following. Either Z belongs to the second derived series, or general torsion order is greater than the twice of the top coefficient, or if general torsion element order is odd, then it is bounded below by the so-called determinant of nodes. Here, by technical reason, I stated the theorem for case Alexander polynomial irreducible, but just taking a irreducible factor, we can say the similar conclusion. And in this theorem, if this or this happens, we are happy because we get some information of the general torsion order. What happens if the first case occurs, namely general torsion element belongs to the second commutator subgroup? Then we iterate the argument repeatedly. Namely, we take a lower central series of commutator subgroup and apply the theorem repeatedly. Then we get Z is I plus first commutator subgroup, or we get a lower bound of general torsion order in terms of some annihilator ideal. Fortunately, for many cases, for some good cases, this annihilator ideal is also understood by Alexander polynomial. This is observed by Perron-Rolfsen, linear diameter Rolfsen. Anyway, homological action is essentially determined by the product of roots of Alexander polynomial. Using this observation, I eventually get this following obstruction of the general torsion order. Not group and general torsion free, and the Alexander polynomial is a product of cyclotomic polynomial. Then this involves some arithmetic, but anyway, we get a lower bound of general torsion order. So this is some kind of generalization of bi-orderability criterion. Bi-orderability criterion says that the non-existence of general torsion element. Here, I provide a slight refinement from Alexander polynomial. If there is a general torsion element, then its order is bounded below from certain kind of information that is obtained from generalized torsion Alexander polynomial. Here is an example. So 2-5 torus node case, applying this theorem, we conclude that the general torsion order 3 element never exists. But general torsion order element 2 actually exists. In a slightly different case, node 10, 1, 3, 2, Alexander polynomial is the same as the torus node, so GK has no general torsion element of generalized torsion order 3. In this case, G does not have a general torsion element of order 2. Okay, in the remaining time, I quickly reviewed some other related results. So, as I said to you, there's a notion of stable commutator length, and which can be used to evaluate or obstruct a generalized torsion element. Here, by a slightly generalization, there's a notion of mixed commutator length and stable mixed commutator length. The stable commutator length, the special case is where n is equal to z. What I observed is that a generalized torsion element, then actually we get a estimate by mixed generalized commutator. I mean, if G is a general torsion element, and assume that we already know that G must belong to the normal subgroup. This situation often happens. In this case, mixed stable commutator length is evaluated. And in particular, it is bounded above by 1/2. Finally, I would like to propose several problems or related notions. Let us consider the general torsion order spectrum of group Z as a set of general torsion order of a group Z. To make comparison, we say that strict general torsion element as general torsion order of non-torsion element to avoid torsion element case. My question is, when these two sets are finite, for example, is general torsion order spectrum is finite if these are three manifold groups, or finitely generated or finitely present group with infinite general torsion order spectrum. How about torsion free case? All the question is a naive question, but I cannot solve it. Here is one interesting observation. For torsion spectrum, namely the set of order of torsion element, then we have one restriction. It is divisor closed. I mean that if PQ is belongs to the torsion spectrum, then P and Q is also torsion spectrum, because GPQ is 1 implies that GPQ is 1. So if PQ is a torsion spectrum, then Q and P are also belongs to the torsion spectrum. However, generalized torsion case, there are no such constraints. For any M, there is a finitely presented torsion-free group such that the generalized torsion order spectrum is exactly M. Here is a construction of such a case. Just I gave an explicit example of group such a case. Due to the time limitation, I skipped detail. But thanks to this observation, now we say that some kind of realization result. Previously, I and Motegi and Teragaito observed that if G and H are torsion free, then the free product of general torsion order spectrum is just a union of each factor. So by taking a free product of previous example, these examples, we conclude that for any finite set, there is a finitely generated, finitely presented torsion free group such that its generalized torsion order spectrum is a given finite set. And of course, infinite case, dropping a finiteness assumption, we are able to realize that any infinite set as a generalized torsion order spectrum. Also, the torsion spectrum, there's a finitely present group whose torsion spectrum is for Zn. And by Higman-Neumann or Higman embedding theorem, we can take an embedding. So by taking an embedding of such kind of group, presumably we are able to realize the generalized torsion spectrum for finitely generated groups, but the problem is that embedding may not preserve the generalized torsion order. So the last question is that assume that there is a map from H to Z. Is there a useful condition that such a map preserves generalized torsion order? Of course, if it's retroact, then it preserves general torsion order. So I would like to know any other useful constraint or useful condition. Okay, this is a summary of my talk. So general torsion element are interesting object, and I present many questions. Maybe I hope that some of you are some of you find that it is easy to solve. So please solve that questions. And indeed, and there are many natural and not explored research directions problem. And so related to bi-orderability and generalizing various properties to torsion element and existence, non-existence criterion and estimate. In particular, I just established a lower bound of generalized torsion orders, but I have no good upper bound. So no, giving some a priori upper bound will be useful. Okay, so let's thank Steve and Adam for organizing such a wonderful workshop. Right.
You know, anything generalized torsion and spatial orderability?
Maybe yes, but I have only little relations. One relation is that from circular ordering, and lifting to the lift to the action of the R real line, you are able to use the translation homomorphism. And one result is that if these are general torsion elements, then translation number is always 0. Yeah, but this is very elemental observation. Besides this elemental observation, I have no substantial result of. But certainly there might be good relations.
So the examples that we know, some of the groups that we know that don't have generalized torsion and not bi-orderable, do we know if those are left orderable or not?
Do you mean
like a handful of examples that we know are like the groups that don't have generalized torsion and they are not bi-orderable?
there are several examples. One example comes from some certain kind of solvable groups, and recently, Akhmedov gave an example of one related groups. So there are examples, but their proof is some kind of ad hoc. So it has a very concrete presentation. So try to find non-existence of general torsion elements by tedious calculations and so on. So it is still mysterious how to construct such a group in general. This no example is all left orderable.